Hello and welcome. Once again coming to you not quite live from One Take Studios, where it's been a while and my camera is already fuzzing out on me. Come on, dude. There we go. Alright, today's topic is logarithmic functions. Logarithmic functions. These things are phenomenal. Just saying that. And I would like you to just open your brain a little bit today because you're going to see some really cool stuff. Alright, so for starters, pondering life. We do know that 2 squared is 4. Yes, duh. Okay. And 2 cubed is 8. Excellent. Wonderful. Okay, so what does that mean about 6? If 2 squared is 4 and 2 cubed is 8, 2 to what power would be 6? Just ponder that for a second. Pick a number. What does your brain come up with? Alright, try something. Go. What'd you think of? Because a lot of people will look at this and say, alright, well, 6 is halfway between 4 and 8. That's logical. So I'm going to pick an exponent that's halfway between 2 and 3. So this must be an exponent of 2.5. Which is really logical if you have something that is linear. These are power functions, exponential functions. These are not linear. And so if you put 2.5 here, it'll be close to 6, but it won't actually be 6. So what is the point of all of this stuff? Well, if you think about, we've talked about inverses in recent videos, and we talk about adding and subtracting being inverse operations, and multiplying and dividing are inverses, and what was the most recent one? Oh yes, that's right. We had rar. Nope, never mind, my brain's gone. Yep, oh, there we go. Like squares and square roots, and cubes and cube roots, alright? Those are all inverses. So if I have something that is exponential, what do I do? How do I undo this? If every other operation has a way to be undone, how do I undo this? Well, ladies and gentlemen, dun 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 dun, that is it right there. Logarithmic functions are the inverses of exponential functions. Logarithms will undo exponential stuff. Alright, the official statement on this topic would be something along the lines of, there we go, but there we go. Alright, so let B and A be positive numbers where B is not equal to 1. Okay, so my base can't be 1. Well, this is the log base B of A equals X, if and only if B to the X equals A. That probably sounds like Greek, and that's okay. Couple things I would like you to know. I did not spell the word if incorrectly. If you heard my phrase, I said if and only if. This is the official mathematical notation for the phrase if and only if. And notice how I read this. Log base B of A equals X. Alright? So this is B to the X equals A, but this is how we are reading this. Log base B of A equals X. If you are anything like me, the first time I saw this didn't mean a single thing to me, and I struggled to keep it in my brain, and I had to pass the Michigan teaching exam for math, and I struggled to keep this in my brain. So I did a bit of work for myself that I'm going to share with you that might help this be a smidge more meaningful. Things that you should know, this right here, this is what's considered to be logarithmic form, and this is exponential form. And again, these two forms are inverses of each other. One of the first things I've done, though, is actually change some of the variables. Depending on which textbook you're looking at, they will use different variables, and they're actually getting closer and closer to the ones that I created for myself, which is something along the lines of what you see at the bottom here. Ladies and gentlemen, this right here, this is my D.A.V.E. Okay, this is my D.A.V.E. right here. What is D.A.V.E., you ask? The Doyle Adapted Version Experience. Yes, Doyle Adapted Version Experience. This is one thing that I created for myself that you will not find in textbooks. And if you say this out loud too many times, people may laugh at you, but that's okay, because you'll actually understand what's going on, unlike some people. Alright, so please notice a couple things here. I have some very similar variables. I use capital letters because I felt like it. Please look at the location. If I'm doing this on a whiteboard, often I will actually draw hand paper, like handwriting lines for learning cursive and learning to write your letters in the first place. But because I have lined paper here, I didn't do that. This is log, it is on the line. The B is a subscript, alright, so that is sitting below the line. A is on the line at proper size, and the P is on the line again at proper size. Compared to here, the B and the A again are on the line, and the P this time is a superscript sitting up and above. So everything is on the line except here the B is sitting lower and here the P is sitting higher. This format makes sense to our brain, and this is why I chose these letters. If I have a base to a power, it will get me this answer. So if I think about what was here, now I'm going to use this one instead. 2 cubed equals 8. If 2 is my base and 3 is my power, well, 2 to the third will give me an answer of 8. All right, so this is something that we are used to seeing. So I took what my brain was used to and put that into this form to give this a little bit more meaning. So what is the base here is still the base here. So this is the base of the exponent. This is the base of the logarithm. So log base b of a. So what was the answer over here becomes like the whatever you want to call it. It doesn't really have a name. I wish it had a name. But this big piece right here, what we are taking the log of, equals p. Well, that's the power that was over here. The entire purpose of a logarithm is to find the power that I would use to put on a base to get a specific answer. In other words, this guy right here. This is saying, I know the base is 2. I know the answer is 6. What I don't know is the power, and the logarithm will help me find that power. How fast can I make my calculator go? I just thought about this real quick. I want to put this together. Can you see my screen? Let's do this. That's a little bit better. Oh, there we go. Okay. So if you'll notice, you have Control, a log button that is right here, and it gives you a place to put in a tiny letter. And so the base for this guy was 2, and so I'm going to put in a 2. And then the answer for this guy was 6, so I'm going to put in a 6. So this says a logarithm is asking 2 to what power would make 6? 2 to what power would make 6? And that's going to be, 2.5 had been our likely guess earlier. We said 2.58496. That's going to actually keep on going for forever and ever. So sorry that wasn't the best graphic, but I did want to show you that. So that is the entire purpose of logarithm, is to find the particular power that creates this for happening. All right, so how will you keep this in your brain? It's catchy, it's dumb and catchy. Log.B.A.P. Ladies and gentlemen, welcome to Log.B.A.P. If you can't remember anything else, just think Log.B.A.P. and that'll tell you how to put this together. That will let you know that you've got the log with the base first and the answer comes next, and the base to some power is going to give us that answer. Well, there's the B.A.P. part of things. There's the power. This helps us find the power. So the purpose of a log is to help find a power. All right, so keeping that in mind, you need to be good at going back and forth between forms. Okay? It's not difficult to do, and it doesn't require a ton of practice, I suppose, but you have to be good at it, because otherwise, again, this is kind of meaningless. So if I'm looking at 3 squared equals 9, well, 3 squared equals 9. This is exponential form. How do I write it into logarithmic form? How do I write it as a log, abbreviated for logarithm? Well, think about it. All right, so I'm trying to write it into log form using my D.A.V.E. here, using Log.B.A.P. I'm going to put log B.A.P. B. B is the base. What is the base? The base is 3. So again, the base sits as a subscript on the line. So log base 3, B.A.P. base answer. What comes next? The answer here was 9. So there we go. So log base 3 of 9, don't let that 9 float. That 9 here is not an exponent for the 3. That's just a plain old 9 with 3 is a subscript for the log. This is saying, 3 to what power makes 9? Well, 3 to what power makes 9? That's 2. So there's the log B.A.P. There's the power portion of things. And that, my friends, right there, that is it. That is it. All right, take a moment. Can you change forms on this one? Give it a shot. Think about it. Have you come up with something? It's going to be similar. Log B.A.P. Log base. What's my base? My base is 5, so I'll put 5 as a subscript there. Base answer. What comes next? This whole thing is my answer. I'm going to put this in parentheses. Do I absolutely have to? No, but it does make things a little bit more readable. This is saying, 5 to what power makes 1 over 125? Well, the power on this thing was the -3, and -3 is it. So this is, this is the logarithmic form for the thing that is sitting right above it in exponential form. And again, this makes sense. 5 cubed is 125, but if we think about our properties of exponents, a negative exponent is a reciprocal. All of this should be logical for your brain, Lord willing. All right, that was so much fun. Let's try it again. Dun, dun, dun. Can you switch forms here? Well, these are in exponential form. So log B.A.P., if I again use my log B.A.P. thing in my brain, I know that this is going to be my base. This is, okay, so the base is going to be 4 base to the power. What does the power have to be? Well, log BAP, the power's at the end, that goes there, and then BAP BA. This is my A, this is my answer. Well, again, if you think about this, this makes sense. Yes, 4 to the first power should be 4, so we're okay with that. That has been changed from logarithmic form into exponential form. All right, ponder this one for a moment. Can you do it? Dun, dun, dun. Okay, again, if we are thinking, this is the base, this is the answer, this is the power, this is our log BAP. So the base is going to be 49, and the power I put on that base is 1/2, and that gives me an answer of 7. There you go. That's what you said, right? Of course you did. And this should make sense once again because we talked about 1/2. If I've got a fraction as an exponent, this is power over root. This is a square root. What's the square root of 49? 7. Logical, always logical, people. All right? Okay. We have a couple of special logs that you should be aware of. And the one is called log base B. Okay. Log base B. Shoot. You know what? Hold that thought for a second. I have 2 special logs and they just got crossed in my brain, and sometimes that happens. I'm scrambling to look something up really quickly. Hold that thought. Thank you for your patience. That's why this is called One Take Studios. And I found it. There we go. Log base B of B equals something. All right, so log base B, so this is called special log of base B. So log base B of B. Think about what this means. This is saying I've got a base of B, and I want to have an answer of B, and what power do I put on a B to make it have a B? Oh, 1. In fact, we just saw this special log right here. So log base 4 of 4 equals 1. Same thing, log base B of B. Anytime these 2 numbers match, the power is going to have to be the 1. That's the only thing I can put on a base to keep it be the same. And so that is one of our special logs. The other special log is called the log of B, which nobody's going to quiz you on these names, so that's going to be quite fine. With this one, it looks slightly different, but similar. We've got log base B of 1 this time. So let's think about this. If my base is B, I'm saying what exponent, what power can I put on a B to make it equal 1? Well, anything to the what power is 1? Ah, yes, did you remember that? This has to be 0. So B to the 0 power equals 1. So regardless of the base, whatever number is here, if this is a 1, this has to be a 0 because this is the only power, the only exponent that we can put on a base to make it equal 1 every single time. All right, so those are a couple of our special logs. All right, other things to keep in your brain. Again, there's just a lot of little things here. Can you please try to use some mental math with me? All right, obviously I can't reach through the screen and see what you are doing, and that's probably good because who wants to do that anyways? But if you just push buttons in the calculator for this, your brain's going to shrivel up and die, all right? This used to be a little bit more tricky as far as using the calculator because I showed you earlier where you could actually type in that little base number to the calculator. Calculators didn't used to have that option. Everything was in base 10, which that's going to come up as being a common log as well because base 10 is going to be something that gets commonly used for other things. But everything is just more flexible these days with the technology that we have. So let us say that we have log base 7 of 343. Again, notice how I read that. You would like to sound intelligent. Log base 7 of 343. How can this be log BAP? It doesn't have the 3 parts. It only has 2 parts. Well, sometimes you might have to just kind of fill in with your brain. That's the base. That's the power. I'm looking for the, that's the base. It's the answer. I'm looking for the power. So if I'm thinking log BAP, base, answer, power, I want to know what power do I put on the 7 to make it equal 343? Excuse me. So my brain is trying to process this. I'm going, okay, so 7 to what power would equal 343? Can you do that in your brain? I don't know. Maybe you can. Maybe you can't. I hope you can, or at least logically. 7 times 7 is 49 times 7. Oh yes, there we go. The answer for that then is 3. Ladies and gentlemen, 3 is the outcome of this, because 7 to the third power would give me 343. Again, we are trying to do this without the calculator, if at all possible, to make sure we actually understand what is happening so that our brain cells grow. Log base 3 of 1/9. Again, if there is nothing on the end, feel free to add something. Maybe I'll just put equals x this time and go straight to the x. But again, I have the base, I have the answer, I'm looking for the power, log BAP. What do you think? Because if I've got, this is saying 3 to some power is going to equal 1/9. All right, I love this because, again, this allows us to use our properties of exponents. What exponent do I stick on a 3 to make it become a 1/9? Well, how do I make a 3 become a 9? 3 squared would do it. And how do I make it flip over? Ladies and gentlemen, x equals -2. Again, 3 squared would be 9, but if I have a negative exponent, that is the reciprocal. All right, so this is a great review of our properties of exponents along the way. I got 2 more here. I know that oftentimes we see decimals and we rejoice, but you may want to think of this in terms of fractions for a moment anyways, and say, okay, so this is, my base is 0.5, that's 1/2, so 1/2. And again, I don't know my power, I'm looking for my power, so maybe I put the parentheses here, equals base answer. This is going to be my answer, 0.25. 0.25 is 1/4. This might be easier for you to see in fraction form and decimal form, or maybe not, that's up to you. But I like this because I can say, hey, I just need to square this. 1/2 times 1/2 is 1/4, x equals 2. 2 is going to have to be my missing power, my missing exponent for this. And last one, again, highly similar for this, saying the same kind of thing. If I've got 1.2, I'm wondering what exponent do I stick on a 1.2? What is the power that will give me an answer of 1.44? So maybe you can actually do this with this. 5 times 5 is 25, 12 times 12 is 144. This also has an answer of 2. Please do not be misled by these examples. The answer is not always 2. All right, so the more that you can do with this in your brain, the better off you're going to be. If you have to use the calculator, seriously, you don't know what's going on. So short term, you'll be rejoicing, yay, it's easy. Yes, but then long term, you'll be like, what the heck is going on? So please attempt to think these through. Okay, last thing that I have for you, very, very last thing here, is going to be this. All right, ladies and gents, finding the inverse of a function, all right? Just briefly for a moment, finding inverses. We said that we switch x and y, so this is really y equals 2 to the x. So if we switch x and y, that means I've got x equals 2 to the y. And we talk about making this look like a function, so we talk about solving for y. But how on earth do I solve for y if it's the exponent? Can I divide by 2? No, that's not going to get rid of the 2. I can't subtract the 2. I can't take the square root. How do I get this down? Guys, what's the inverse of exponential? The inverse of exponential is logarithm. Switch the form, change forms. All right, so all of a sudden, if I'm looking at this and thinking in terms of a log base, well, what's my base? My base is 2, so log base 2, let's see, base answer, answer. Ooh, this had an answer of x, and then equals log BAP, base answer power, the power was y. Oh look, magically just by changing forms, I have the y by itself, ladies and gents. So we are saying that log base 2 of x is going to be the inverse function. All right, the inverse function of 2 to the x. I want you to see what this looks like as a graph. So I'm going to switch screens here. We've got this. I have already graphed 2 to the x. So let's enter a second graph here, shall we? Hitting tab. I don't want a third graph, silly. I want a second graph. Oh, that's right. Sorry. I have that on a different screen. Maybe I do want a third graph. Okay, I'm going to go back down. Third graph for this one, ignore the second graph, that's something else. With this, we are saying that we want to do log. So again, control log. There we go. Base, well, we just said that the base should be 2. Base should be 2. Base should be 2. Why are we not having a 2? 2 ha, of x. And that's going to go there then. There we are. Alright, and I hit graph. What do I see? Ladies and gentlemen, let's go for one more graph, shall we? Just the line y equals x. And enter. There we go. What did we say about inverses? Moving my labels so I can read this a little bit better here. There we go. If you think about what we said about inverses, the line y equals x, this perfect line right here, is a line of symmetry. We can see the clear symmetry with this. Again, the idea of inverse is x and y switch. That is the foundation of all things inverse, x and y switch. So while the first graph, the exponential graph, had a y-intercept of 1, the logarithmic graph has an x-intercept of 1. The exponential graph had an asymptote on the x-axis. Again, despite the fact what this looks like, this is approaching the x-axis and getting closer and closer for all eternity. Well, if the asymptote here is the x-axis, then for its inverse, this has an asymptote on the y-axis. And again, we can see it getting closer and closer for all of eternity. So x's and y's switch place. We can even have this conversation down to domain and range. All right, think about this guy for a second. Domain, the x's, it'll go forever to the left, there's nothing stopping it. And while this does appear to go up, it is also moving outward as it goes. So there's actually nothing stopping my x values here too. Left and right, this thing goes on forever and forever and forever. But the range for this, everything is above 0. All right, so I'm going to switch my screen back real quick so we can make a note of that. And we are saying that for the original function, oops, did I switch my screen? This one, there we go, this one. We're saying that this thing had a domain, can I squeeze this? You haven't seen this format in a while, I don't think, of x's such that x is a member, oh, squishy, of the set of real numbers. Can you read that? You probably can't read that, I'm sorry. X is such that, again, the down bar is such that x is a member of the set of real numbers. The x's continue for forever and ever and ever. However, for the range for this original guy, what we are saying is that all the values are above 0. So it's the y values such that y is greater than 0. And my set notation right there. All right, so again, if x and y switch places, what's going to be true over here? These guys are just going to be reversed. All right, they are just going to be reversed. So when we're talking about this one, I'm going to switch colors, see if that clarifies things slightly. We'll do this, no, inverses. So this is going to be my domain over here. Well, what was the range for this one? This time we're saying the x is such that the x's are greater than 0. Okay, logical, hopefully. And then the ranges are going to be the y's such that we're talking the y's that are members of the set of real numbers. In other words, all real numbers. So what was domain here is range here. What was range here is domain here. And again, one last time, we can actually see that on our graph as well. All right, so we had said that for the inverse, that the x's were going to be greater than 0. So here's my x-axis. Everything is to the right of the x-axis, so my x's are greater than 0. And my range is all real numbers. This will go down for all of eternity on the y-axis, and it will go up. Again, I know it appears to be going to the right, but it's also going up as it goes. So the range is all real numbers. All right, so a lot to think about, but really not a lot that's complicated, just a lot that's new for your brain. Whew. All right, take a deep breath, play with it, and enjoy. Thanks.